video, I'm gonna show you the size of Graham's number. For those of you who've never heard it before, it's a lot bigger than you think. This number is defined as the biggest number used in a mathematical equation. But how big is it exactly? It's basically a bunch of 3's multiplied out. Let's have 3 arrow 3. That's just the same as saying 3 to the power 3. 3 to the power 3, that's equal to 3 times 3 times 3, which is equal to 27. Now let's have 3 double arrow 3. 3 double arrow 3 can also be written like this. 3 double arrow 3 is equal to 3 arrow 3 arrow 3. 3 to the power of 3, that's equal to 27. 3 to the power of 27, that's 7.6 trillion. What about 3 triple arrow 3? That's equal to 3 double arrow 3 double arrow 3. 3 double arrow 3, as we've known earlier, is equal to 7.6 trillion. 3 double arrow 7.6 trillion. 3 arrow 3 arrow 3 arrow 3 arrow 3 7.6 trillion times. And finally, we have 3 4 arrows 3. That's equal to 3 triple arrow 3 triple arrow 3. 3 triple arrow 3, that's 3 to the power 3 7.6 trillion times. 3 triple arrow, this giant number, how that look like? Because we have 3 arrows in our operation, we do the repeated 2 arrows. And how many times do we do it? This gigantic number of times. Let's evaluate them, shall we? 3 double arrow 3, as we've known earlier, is equal to 7.6 trillion. 3 double arrow 7.6 trillion. You keep iterating these power towers 3 triple arrow 3 times. 3 4 arrows 3 is also known as G1. And then we have G2. That's equal to 3, but with how many arrows? 3. It has G1 number of arrows, or this many arrows. G3 has G2 number of arrows. G4 has G3 number of arrows. You keep incrementing all the way to G64, which is 3 with G63 arrows to 3. G64 is Graham's number. to create bigger numbers, we need faster growing functions. 2 plus n is an example of a function. But 2 times n grows faster than 2 plus n. But 2 to the power of n grows even faster. And in our previous video, we did the up arrow notation, where adding just one arrow increased the operation drastically. This allowed us to make much larger numbers. But what if we wanted to go bigger? Bigger than any number up arrow notation can make. With a fast growing hierarchy, we can easily exceed Graham's number. But before we get too big, let me first introduce you to the basics. We have f. This denotes a function. And then we have alpha. This is the level of the function. And then we have n. This is the number we're going to input the function to. Let's have the first level, which is 0. That's f0 of n, which is equal to n plus 1. So if n equals 3, it's equal to 3 plus 1. If n equals 100, that's equal to 100 plus 1. Now let's have the next level, which is 1. f1 of n is equal to 2 times n. f2 of n is equal to 2 to the power of n times n. But what about f3 of n? That's equal to f2 of n with n repetitions of the f2 function. Let's have f3 of 2. That's equal to f2 of f2 of 2 with 2 repetitions. f2 of n, as we remember earlier, is equal to 2 to the power of n times n. f2 of 2, 2 to the power of 2 times 2. 2 to the power of 2, that's equal to 4, times 2, that's equal to 8. f2 of 8, 2 to the power of 8 times 8. 2 to the power of 8, 256, times 8 is 2048. But what about f3 of n when n is equal to 3? That's f3 of 3. Because we have 3 as n, we do the f2 process 3 times. f2 of 3 is 2 to the power of 3 times 3, which is equal to 24. f2 of 24 is 2 to the power of 24 times 24, which is 402 million. Now f2 of 402 million, that's 2 to the power of 402 million times 402 million. That's around 121 million digits. But we're only the third level. If we do f4 of 3, that's going to be the f3 process 3 times. In general, we can say that f alpha of n is equal to f alpha minus 1 of n repeated n times. You can keep increasing the level like this, but no matter how big the number is, it won't get as fast as Graham's function. Let me kind of show you why. f0 of n is equal to n plus 1. It resembles addition. f1 of n is equal to 2 times n. This resembles multiplication. Now f2 of n is equal to 2 to the power of n times n. This resembles exponentiation. f3 of n resembles 2 arrows. As you can see, the higher the level we get, the more arrows it adds to our operation. That's why it won't get as fast as Graham's function. Graham's function is defined as g sub n is equal to 3 with g sub n minus 1 arrows, where g1 is 3 with 4 arrows to 3. So, if we can't grow as fast as Graham's function no matter how big of a level we get, why are we using this notation? I said a while ago that we can easily surpass Graham's number. Yes, we can, not just with finite numbers. This is when omega comes in handy. Omega is our first infinite ordinal. When we say ordinal, we're talking about the order. Omega comes after all the natural numbers. It's also our first limit ordinal. When we say limit ordinal, nothing comes before it. So how exactly do we use something like this in the fast-growing hierarchy when our level is equal to omega? There's this thing we call diagonalization. We have f1, f2, and f3. We have 1, 2, and 3. f1 of 1, that's equal to 2. f1 of 2, that's equal to 4. f1 of 3, that's equal to 6. f2 of 1, that's equal to 2. f2 of 2, that's equal to 8. f2 of 3, that's equal to 24. f3 of 1, that's 2. f3 of 2, that's 2048. f3 of 3, that's 121 million digits. Going diagonal gets you really big numbers. F omega of 1, F omega of 2, F omega of 3, so on and so forth. F omega of n is equal to Fn of n. So F omega of 100, that's equal to F100 of 100. And then we have omega plus 1. Omega plus 1 is not bigger than omega. It just comes after omega. Remember, omega is an ordinal. So we're talking about the order. Let's say f omega plus 1 of 3. Remember, we did the previous operation. So what comes before omega plus 1? That's omega. So we do the F omega process 3 times. F omega 3, as we've known earlier, is the 121 million digit number. Now F omega of 121 million digit number, that's F 121 million digits of 121 million digits. This is insanely big. Now F omega of insanely big, that's F insanely big of insanely big. We can have omega plus 2, omega plus 3, omega plus 4, so on and so forth. And then we have our next limit, which is omega plus omega, which can also be written as omega times 2. I'll leave this for the next video. In our previous video, we've had diagonalization, where we pick numbers in a diagonal path using omega. Then we had omega plus 1. We're inputting even a small number such as 3 yields such a massive number. In this video, I'm going to show you guys more information about omega, as they will be important later on. 1 plus omega is not the same as omega plus 1. Let me show you why. Let's say we have an infinite number of balls. This is omega. When we do 1 plus omega, we're just adding 1 ball to the infinite number of balls. So that doesn't make it different from infinity. But when we do omega plus 1, we're adding 1 ball after an infinite number of balls. We add 2 balls after an infinite number of balls. That's omega plus 2. Omega plus 3, omega plus 4, omega plus 5, omega plus 6, omega plus 7. We can even have an infinite number of balls after an infinite number of balls, which we know as omega times 2. Now that we know how ordinals are counted, let's get back to the fast-growing hierarchy. F omega plus 1 of n already grows faster than Graham's function. So F omega plus 1 of 64 is a lot bigger than G64, which is also known as Graham's number. Now, just how much faster would F omega times 2 of n be? But first, let me show you how to break down omega times 2. Omega times 2 breaks down into omega plus omega. Now pay attention to this omega. This is the closest omega to n. You diagonalize omega by turning it into an n. Now we have omega plus n of n. Let's have f omega times 2 of 3, for example. You turn omega times 2 into omega plus omega, and then you turn the closest omega into a 3. From here, we can break this down into 3 copies of omega plus 2. F omega plus 2 of 3, we break it down into 3 copies of omega plus 1. Now F omega plus 1 of 3, as we did in an earlier video, we break it down into 3 copies of the F omega function. This whole thing was an unimaginable number. Now F omega plus 1 of this unimaginable number, just like how we broke F omega plus 1 of 3, we do f omega of f omega of f omega of f omega unimaginable number of times. Put it back into the parenthesis, and then you do f omega plus 1 of it. We keep evaluating these functions until we reach the end. But all of this is nothing compared to omega times 2 plus 1. Let's have f omega times 2 plus 1 of 3, for example. Now what comes before omega times 2 plus 1? That's omega times 2. So you do the omega times 2 process 3 times. F omega times 2 of 3, you break it down into omega plus omega, and then you turn the closest omega into a 3. F omega times 2 of f omega plus 3 of 3, you break omega times 2 into omega plus omega, and then you diagonalize it to f omega plus 3 of 3. F omega times 2 of this massive number, we break omega times 2 into omega plus omega, then we diagonalize once again. We can do omega times 2 plus 2, omega times 2 plus 3, so on and so forth. And then we'll reach our next limit, which is omega times 2 plus omega, which can also be written as omega times 3. Let's have f omega times 3 of 4, for example. We break f omega times 3 into omega times 2 plus omega, and then we diagonalize omega to 4. If we do f omega times 100 of n, we break it down into f omega times 99 plus omega, and we diagonalize omega to n. We can keep multiplying omega like this, and then we'll reach our next limit, which is omega times omega, which can also be written as omega squared. Let's have f omega squared of n. We turn omega squared into omega times omega, and then we turn the closest omega to n. So we have omega times n of n. But things get much more serious with omega cubed. Let's have f omega cubed of 3. We can break omega cubed into omega times omega times omega. And these two omegas, you group them as omega squared. And this turns into omega squared times 3, which can be broken down into omega squared plus omega squared plus omega squared. Omega squared plus omega squared can be grouped as omega squared times 2. Omega squared, as we've known earlier, breaks down into omega times 3. Omega times 3 breaks down into omega times 2 plus omega. And now omega gets diagonalized to 3. This is the simplified version of omega cubed. We can have omega to the 4th, omega to the 5, omega to the 6, omega to the 7, omega to the 8th, omega to the 9th, and then we reach our next limit, which is omega to the omega. Let's have f omega to the omega of 4. That turns into omega to the 4th. Then you break it down to omega cubed times omega. Then the closest omega turns into a 4. You turn omega cubed times 4 into omega cubed times 3 plus omega cubed. You turn omega cubed, omega squared times omega. This turns to omega squared times 4. Omega squared times 4 turns into omega squared times 3 plus omega squared. Then omega squared turns into omega times 4. Then finally, omega times 4 turns into omega times 3 plus omega. And then the closest omega, you turn into a 4. This is how intense f omega to the omega is. But we can even go bigger. We can have omega to the omega to the omega. We can keep exponentiating omega really. And the limit of this is epsilon naught, which is our next infinite ordinal after omega. We had omega to the power of omega an infinite number of times. This is equal to epsilon naught. The counting sequence for epsilon naught is 1, omega, omega to the omega, omega to the omega to the omega, so on and so forth. So f epsilon naught of 1 is equal to f1 of 1, which is equal to 2. Because we have 1 as our input, we pick the first element of the counting sequence. Now f epsilon naught of 2, you pick the second element of the counting sequence, which is omega. And this turns into f2 of 2, which is equal to 8. But f epsilon naught of 3 turns into f omega to the omega of 3. This turns into f omega cubed of 3, which we've known in our previous video expands to this monstrosity. But f epsilon naught of 4 is equal to f omega to the omega to the omega 4. The uppermost omega gets diagonalized into a 4, and then omega to the 4th, as we've known in our previous video, expands to an even bigger monstrosity. In general, we can say f epsilon naught of n is equal to f omega to the omega to the omega to the omega n minus 1 times. Omega to the epsilon naught is just going to equal epsilon naught. This is our first fixed point, because omega to the epsilon naught is just omega to the power of an infinite number of omegas. So adding 1 omega to the infinite stack of omegas won't be different from an infinite number of omegas. So, is epsilon naught our biggest number? Can we not go bigger? Actually, we can. We can do epsilon naught plus 1. Let's have f epsilon naught plus 1 of 3. This breaks down into 3 copies of the f epsilon naught function. F epsilon naught of 3, as we've known, is f omega cubed of 3. Now f epsilon naught of f omega cubed of 3, that's f omega to the omega to the omega to the omega, f omega cubed of 3 minus 1 times. And then finally, we do f epsilon naught of this whole thing. We can't get bigger with omega to the epsilon naught, but we can get bigger with omega to the epsilon naught plus 1. By the rule of exponents, this is equal to omega to the epsilon naught times omega to the 1, or simply just omega. And this thing right here collapses into just epsilon naught. Now we have epsilon naught times omega. We can have omega to the epsilon naught plus 1. We can have an infinite tower of omegas exponentiated with epsilon naught plus 1 on top. This sequence is called epsilon 1. This is the same as an infinite exponentiation of epsilon naughts. The counting sequence for epsilon 1 is omega to the epsilon naught plus 1, omega to the mega to the epsilon naught plus 1, omega to the mega to the mega to the epsilon naught plus 1, so on and so forth. Let's have f epsilon 1 of 3. That's equal to f omega to the mega to the mega to the epsilon naught plus 1 of 3. You turn omega to the epsilon naught plus 1 into epsilon naught times omega. Then you diagonalize omega into 3. This turns into epsilon naught times 3. You turn epsilon naught times 3 into epsilon naught times 2 plus epsilon naught. And then epsilon naught of 3, as we know, turns into omega cubed. Now omega to the power of this whole thing right here, we do the rule of exponents once again. And then omega cubed gets expanded. But we have one last omega here in the bottom. Now you can imagine how many steps it will take to break down. We can do epsilon 1 plus 1. We can even have an infinite tower of omegas with epsilon 1 plus 1 at the top. This sequence is called epsilon 2. If we have omega to the mega to the mega to the mega with epsilon 2 plus 1 at the top, this is called epsilon 3. We can keep increasing the index of epsilon. Yes, we're allowed to use omega. We can even have epsilon naught as our index. We can keep nesting epsilon naught an infinite number of times. Then we'll reach our next infinite ordinal, which is zeta naught. That's it for today's video. I hope you all enjoyed. Zeta naught. Zeta naught can be seen as an infinite nesting of epsilons. The counting sequence for zeta naught is equal to epsilon naught, epsilon epsilon naught, epsilon 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 naught, so on and so forth. Let's have f zeta naught of 3. This is equal to f epsilon 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 naught of 3. Epsilon naught turns into omega to the omega, and then it expands to omega cubed. Now pay attention to the simplified omega cubed. This is the index of epsilon. Let's focus on epsilon omega cubed first. So how do we break this down? Remember how epsilon 1 of 3 was broken down. You turn it into omega to the mega to the mega to the epsilon 0 plus 1 of 3. So epsilon omega cubed turns into omega to the mega to the mega to the epsilon, but with what index? Because we have a plus 3, this reduces into just plus 2. This becomes the index of epsilon. Don't forget plus 1. We plug this whole thing as the index of epsilon. If we plug zeta naught as our index of epsilon, this will just equal to zeta naught. Because zeta naught is just an infinite nesting of epsilons. This is the fixed point of epsilon. We can do zeta naught plus 1. Let's have f zeta naught plus 1 of 3. This breaks down into 3 copies of the f zeta naught function. F zeta naught of 3, as we've known earlier, expands to this giant monstrosity. f zeta naught of this giant monstrosity, that's equal to f epsilon epsilon epsilon, but with how many epsilons? This many epsilons. Now if zeta naught of this whole thing, that's equal to f epsilon 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 with this many epsilons. We can't get bigger with epsilon zeta naught, but we can get bigger with epsilon zeta naught plus 1. We can have epsilon epsilon zeta naught plus 1, epsilon 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 zeta naught plus 1, and so on. This sequence is called zeta 1. This is an infinite nesting of epsilons with zeta naught plus 1 at the bottom. The counting sequence for zeta 1 is equal to epsilon zeta naught plus 1, epsilon epsilon zeta naught plus 1, epsilon 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 zeta naught plus 1, and so on. Let's have f zeta 1 3. This is equal to f epsilon 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 zeta naught plus 1 of 3. Let's focus on epsilon zeta naught plus 1 first. This breaks down into omega to the omega to the omega to the epsilon zeta naught plus 1. Now epsilon zeta naught, as we've known earlier, collapses into just zeta naught. And then we do the rule of exponents similar to the previous video. And then omega to the zeta naught collapses into just zeta naught. Now omega gets diagonalized into a 3. This becomes zeta naught times 3. Zeta naught times 3 breaks down into zeta naught times 2 plus zeta naught. And then zeta naught of 3, as we've known earlier, expands to this giant monstrosity. But this is just zeta 1 of 3. But we can have zeta 2, zeta 3, zeta 4, and so on. We can even have omega as our index of zeta. We can also have epsilon naught. We can even do zeta to the zeta naught. We can keep nesting zetas like this. An infinite nesting of zetas is called eta naught. This is the fixed point of zeta. In our previous video, we've had various ordinals, such as omega, epsilon, zeta, and eta. But we can only declare new ordinals so many times. We don't have an infinite number of letters. So we're going to use a new notation. We have phi. Then we have alpha. This is the level of the ordinal. We'll get into that later. Let's have phi alpha when alpha is equal to 0. That's phi 0. Phi 0 is equal to omega. Open and close parenthesis. Let's just have an x. This is the index of omega. When alpha is equal to 1, that's phi 1x. This is equal to epsilon sub x. Then phi 2x is equal to zeta x. To recap all of this, phi 0 is equal to omega. Phi 1 is equal to epsilon. Phi 2 is equal to zeta. And don't forget their index. Phi 3 is equal to eta. Phi 4, that's an infinite nesting of etas. This is also called the eta fixed point. we can keep increasing the index of phi. This way, we are effortlessly creating bigger ordinals. Remember, omega is just equal to phi 0, and epsilon is just equal to phi 1. So how do we use phi alpha of x in the fast-growing hierarchy? We simply plug it under f. Alternatively, it can also be written like this. Let's go over to the rules. Let's have phi alpha x of n when x is equal to 0. You do phi alpha minus 1 n times. Let's have phi 1 0 of 2. Because we have phi 1, we do the phi 0 process. We do it 2 times. Phi 0 of 0, that's equal to omega to the 0. Any number raised to 0 is equal to 1. Phi 0 of 1 is equal to omega to the 1. Any number raised to the power of 1 is just the number itself. Omega diagonalizes into a 2. This becomes f2 of 2, which is equal to 4. If we did phi 1 of 3, that's going to be 3 copies of the phi 0 function. This is equal to f epsilon naught of 3. But what about phi alpha x of n when x is greater than 0? We also do n copies of phi alpha minus 1. And inside this open and closed parenthesis is phi alpha. And then we have x minus 1. And then we add a plus 1. And let's not forget n. Looks too cryptic? Let's have an example. Let's have phi 1 1 of 3. We do 3 copies of the phi 0 function. And inside this parenthesis, we do phi 1. Because we have 1 as our value of x, it reduces into a 0. And then we add a plus 1. As you can see, this resembles omega to the omega to the omega to the epsilon 0 plus 1. And as we've known in our previous video, this turns into omega to the epsilon naught times omega. So phi 0, phi 1 0 plus 1 turns into phi 0, phi 1 0 times omega. Omega to the epsilon naught collapses into just epsilon naught. So phi 0, phi 1 collapses into just phi 1. So that's phi 1 0 times omega. Omega diagonalizes into a 3. So phi 1 0 times 3 breaks down to phi 1 0 times 2 plus phi 1 0. I'll just halt right here. I forgot to mention, but we can even have phi omega. We can also have phi epsilon naught, phi zeta naught, phi eta naught. We can even have an index of phi 0 of 0. We can even nest phi functions like this an infinite number of times. This new sequence is called gamma naught. We have gamma naught. Gamma naught is equal to an infinite nesting of phi functions. The counting sequence for gamma naught is equal to phi 0 of 0, phi of phi 0 of 0, phi of phi of phi 0 of 0, and so on. Let's have f gamma naught of 3. That is equal to f with an index of phi of phi of phi 0 of 3. Phi 0 of 0, as we've known earlier, is equal to 1. Phi 1 of 0 is equal to epsilon 0. And epsilon naught of 3, as we've known, expands to omega cubed. And then finally, we have phi omega cubed. Now this is extremely big. Now we can get bigger with gamma naught plus 1. Let's have f gamma naught plus 1 of 3. This breaks down into 3 copies of the gamma naught function. F gamma naught of 3, as we've known, is equal to phi omega cubed 0 of 3. Now f gamma naught of this whole thing, that's phi of phi of phi of phi, f gamma naught of 3 times. Now f gamma naught of this whole thing, this is a lot bigger. We can get bigger with gamma 1. The counting sequence for gamma 1 is equal to phi gamma naught plus 1, phi of phi gamma naught plus 1, phi of phi gamma naught plus 1, and so on. We can have gamma 2, gamma 3, gamma 4, gamma omega, or even gamma to the gamma naught. We can even have an infinite nesting of gammas. This is the gamma fixed point. You can keep going higher by creating new fixed points. This video, we're gonna go beyond gamma naught. We're gonna use extended Veblen notation. Phi alpha of x can also be written like this. Phi 1 of x, that's equal to epsilon sub x. Phi 2 of x, that's equal to zeta sub x. Phi 3 of x, that's equal to eta sub x. It just goes higher from here. But no matter how big our alpha is, it will always be lesser than gamma naught. So we add another variable. Gamma naught can also be written as phi 1, 0, 0. If we change the third argument to x, this will equal to gamma x. If we change the second argument to 1, this will be an infinite nesting of gammas. Let's just call this beta x. If we change it to 2, this will be an infinite nesting of betas. We can keep increasing, but this will eventually run out of power. So now we increase the first argument. This will eventually run out of power, so we add more arguments. If we plug this under the fast-growing hierarchy, this will be almighty. But there's something even bigger. The small Veblen ordinal, or SVO for short. The counting sequence for SVO is equal to phi 1, 0, phi 1, 0, 0, phi 1, 0, 0, 0, and so on. So FSVO of 4 is equal to phi 1, 0, 0, 0, 0. The small Veblen ordinal is phi 1 followed by a mega number of arguments. Then we have the large Veblen ordinal, which is 1 followed by this many arguments. The large Veblen ordinal has a mega number of nestings. In this video, we're going to be talking about ordinal collapsing functions. Let's have the set S. This contains the elements 0, 1, omega, and capital omega. And then we have the set C0. This contains addition, multiplication, and exponentiation. I'll call that AME for short. We do AME to the elements of set S. But we can only do it a finite number of times. And then we have psi x. This is defined as the smallest ordinal, which is not a member of Cx. Because we have C0, we have the psi 0. Let's see which ordinal is not a member of C0. We have 1, and we can perform addition to it a finite number of times. But luckily, we have omega. We can add omega, we can multiply omega, and even exponentiate omega, but only finite number of times. If we exponentiate omega to itself an infinite number of times, we get epsilon naught. So epsilon naught is our first ordinal not constructible with C0. So this is our psi 0. If we have C1, this will contain C0 in union with psi 0. What this means is that we have the AME of all the elements of C0, including psi 0. We can add psi 0, we can multiply psi 0, and we can even exponentiate psi 0, but only finite number of times. And as we've known, psi 0 is the same as epsilon 0. If we exponentiate epsilon naught an infinite number of times, this creates epsilon 1. So this is our psi 1. If we do C2, this will include everything in C1, including psi 1. In general, we can say that Cx contains everything all the way to psi x minus 1. If we do C omega, this will contain all the psi's of the finite numbers. If we do C omega plus 1, this will contain everything up to psi omega. If we do C zeta naught, this will contain all the finite nestings of epsilons. Now we can create psi zeta naught, right? Wrong. Because zeta naught itself is not a member of C zeta naught. C zeta naught contains only up to series of nested epsilons, but not zeta naught itself. So if we do psi zeta naught or higher, this will just equal to zeta naught. So how do we get bigger if zeta naught is the limit? Let's take a look at capital omega. Capital omega will always be a member of set C. So if we do C omega, this will also only contain up to the finite nestings of epsilons. Because omega is a member of set C, we can create psi omega. This is also going to be just equal to zeta naught. If we do psi omega plus 1, this is going to be equal to epsilon zeta naught plus 1. If we have a plus 2, this will be epsilon zeta naught plus 2. If we do psi omega plus A, this is equal to epsilon zeta naught plus A. But this only works when A is lesser than zeta 1. So we add another capital omega to create zeta 1. If we do omega times 2 plus 1, we will have epsilon zeta 1 plus 1. If we add another omega, this will create zeta 2. This can also be written as omega times 3. If we do omega times a, this will be zeta a minus 1. But if we multiply by an ordinal, the index will be the ordinal itself. But if we want an infinite nesting of zetas, we multiply by omega. This can also be written as omega squared. This is also equal to eta naught. If we do omega cubed, this will be an infinite nesting of etas. This can also be written as 540. So if we do psi omega to the a, we get phi a plus 1, 0. But if we want an infinite nesting of phi's, we exponentiate it to omega. If we do omega to the omega times a, this is equal to gamma a minus 1. If we want an infinite nesting of gammas, we multiply it by omega. Because we have 1 as our exponent of omega, this can be written as omega plus 1, according to the rule of exponents. If we do omega to the omega plus a, this will be phi 1a 0. If we do omega times a, this will be a 0, 0. If we multiply it by omega, we add another argument. If we do omega cubed, we add another argument. If we have lowercase omega as our exponent, this will have omega arguments. This is also known as the small Veblen ordinal. If we put capital omega as our exponent, this will be the large Veblen ordinal. We can keep exponentiating omegas like this, but only a finite number of times. If we do it an infinite number of times, we reach our next ordinal, which is the Bachman-Howard ordinal, or BHO for short. Before we get any further, I'm going to show you how to break these down into fast-growing hierarchy. Let's have psi omega first. Let's just have a value of 3. But before we break this down, we first need to know the counting sequence of psi omega. The first element is psi 0. The second element is psi omega. But instead of a capital omega, we replace it with the previous element of the counting sequence, which is psi 0. Now the third element is psi omega, except omega is replaced by the previous element. This series continues on like this. Now going back to the fast-growing hierarchy, we diagonalize it with the third element of the counting sequence. Psi 0, as we know, is equal to epsilon 0. And as we know, epsilon naught of 3 is omega cubed of 3. Now psi omega cubed is epsilon omega cubed. I'll just halt right here. Now let's have psi omega squared. Now let's determine the counting sequence of psi omega squared. The first element is psi 0. Now the second element is psi omega squared. Now let's do some simplification here. We know that omega squared is the same as omega times omega. Now this omega right here, you replace it with the previous element of the counting sequence. Now the third element, which is psi omega times omega, now omega is replaced by the previous element. Now let's translate these into ordinals. Psi 0 collapses to epsilon 0. Now what about psi omega times psi 0? Remember in our previous video, we said that psi omega times a is equal to zeta a minus 1. Because we have omega times psi 0, this collapses into zeta epsilon naught. Now psi omega times zeta epsilon naught, Now this collapses with zeta with the subscript of zeta epsilon naught. In our previous video, we have known that psi omega squared is equal to eta naught. But notice that their index is epsilon naught. Psi omega squared resembles eta naught, but is not equal to eta naught. So we still have to use the respective element. Now let's have psi omega to the omega to the omega. As usual, the counting element starts with psi 0. The second element is psi omega to the omega to the omega, with the uppermost omega being replaced by the previous element. The third element is psi omega to the omega to the omega, with the uppermost omega being replaced by the previous element. Now let us zoom into this monstrosity. Psi 0, as we've known, we break it down to omega cubed. Now we do the rules of exponents. I'll just stop right here as it gets really complicated. Now the counting sequence for the Beckman-Howard ordinal is psi omega to the omega, psi omega to the omega to the omega, and so on. The Beckman-Howard ordinal can also be written like this. Now no need to worry why it looks like this. This is just the same as an infinite exponentiation of capital omegas. This can also be written as psi 1 0. If we do psi 1a, this will be equal to epsilon omega plus 1 plus a. If we do psi 1 capital omega, this will be zeta omega plus 1. If we do psi 1 omega times a, this will be zeta omega plus 1 plus a. If we do psi 1 omega to the omega times a, this will be gamma omega plus 1 plus a. We can also exponentiate capital omegas infinite. This is just the same as an infinite exponentiation of capital omegas. This can also be written as psi 1 0. If we do psi 1a, this will be equal to epsilon omega plus 1 plus a. If we do psi 1 capital omega, this will be zeta omega plus 1. If we do psi 1 omega times a, this will be zeta omega plus 1 plus a. If we do psi 1 omega to the omega times a, this will be gamma omega plus 1 plus a. We can also exponentiate capital omegas infinitely. This will be psi 1 epsilon omega plus 1. This can also be written as psi 2 0. We can have psi 3, we can have psi 4, we can keep incrementing the subscript of psi. We can even do stuff like psi omega. Let's have psi omega 3. Omega, as we know, turns into a 3. We break this down into psi 2 epsilon omega plus 1. This also turns into omega to the omega to the omega. Now this breaks down the same way we did a while ago, except now the psi's have a subscript of 2 instead of just a plain psi. We can even have stuff like psi gamma naught, or we can even have an infinite nesting of psi functions.